Thank you. Right, I got some emails, so thank you for people who emailed. Oops. Okay. So So today, and perhaps on Wednesday as well, we're going to go in a slightly different direction. Instead of talking about very dense graphs, we're going to talk about very sparse graphs, so graphs with very few edges. And the simplest kind of graph with very few edges is a tree. So what is the definition of a tree? Well, let's draw a picture of a tree, and then maybe we can try and come up with a definition together. So here is a tree. It's got a root, and it's got like a trunk, and then maybe some branches. Okay, there's a picture of a tree. So what is a tree? So, yeah, if you really know, then I think you can say. So what are the properties? This is a graph that looks like a tree. What properties does it have?
No cycles.
No cycles, right? Trees don't have cycles. Right? You don't go down two branches and come to the same branch. So, a tree is a graph Is that enough?
No, connected.
And connected. Right. I'm going to rub out this branch so I can write. Okay. Is that enough? Yeah, it seems pretty reasonable. Right. I'd like to suggest an alternative definition. Perhaps it's not so obvious to guess. So this is equivalent to a maximal graph without cycles. And it's also equivalent to a minimal connected graph. Maximal, minimal means in terms of adding and removing edges. So if you've got a graph with no cycles and any edge creates a cycle, that's a tree. If you've got a graph that's connected and any edge you remove disconnects it, that's a tree. Okay? These are all equivalent definitions. It's a simple exercise to show that they're all equivalent. Okay? So I encourage you, if you haven't seen this stuff before, to go home and verify for yourself these really all mean the same thing. Okay. So what questions can we ask about trees? How about what can we say about the extremal number of t? So I think this is not completely obvious. So perhaps the lower bound might be easier. What lower bound can you give? I mean, lower bound just means a construction. So give me a graph without a copy of t on n vertices, right? So k, let's think of k as being fixed. And let's think of n going to infinity. Okay, so k is 10 to the 10, and n is 10 to the 10 to the 10 to the 10. Okay? You want to find a copy of t inside a graph at n vertices. So how many edges do you need? So if the first question is, can you give me a graph with a reasonable number of edges without a copy of t? So what's the best you can do? Okay, so I'll go with yeah, so you click it. Okay.
Lots of k minus 1 potatoes.
Right, there we go. Potatoes are a good idea. Right, none of these contains t, because t is connected. It doesn't fit in any of them. Right? You can't use two vertices from different potatoes. And how many edges does this have? Well, it's got k minus 1 choose 2 in each part. And it's got n divided by k minus 1 parts. Again, let's not worry about the error in case k minus 1 doesn't divide n. So roughly this many edges, which equals k minus 2 times n over 2. So it's at least k minus 2 times n over 2, maybe minus a tiny bit in case you've got some vertices left over, but let's not worry too much. Okay, so what upper bound can we give? Or can you give a better lower bound? So it doesn't seem very easy. So let's see if we can prove suppose some constant times n. Did anyone think about the homework problem? Anyone come up with a conjecture?
I come up with the conjecture that trees were forests, like units of trees were listed.
Yeah, very good. So that is in fact the right answer.
Yeah.
So exactly. So the extremal number turns out to be linear in n if and only if the graph does not have a cycle. So maybe we'll prove that. Maybe we'll prove it today. Maybe I'll prove it. Okay, let's prove it now. Why not? Okay, so this is true for some c that depends on t. C depends on k. So let's prove this. So how are you going to go out finding a tree in a graph with, say, so you look at this tree, it's on, let's say, 100 vertices. You've got some graph whose average degree is 10 to the 10 to the 10, but it's got way, way more vertices than that. How are you going to find this tree inside it? Well, one thing you might do is just, I mean, if you were given a tree and you said try and find it, you might just try and do it, right? So you might say, let's pick a vertex of our big graph G. So let's suppose the edges of G is this large constant times k of k, so a large constant depending on k times n. So the average degree in this graph is this large constant, right, up to a factor of 2. So if you pick like a typical vertex, it's going to have lots and lots and lots of neighbours. So you could just take, and you've got this tree that you're trying to put in it. Okay, maybe this one. You could just say, okay, let's just stick this vertex here. Right, we're trying to embed this tree in this graph, so just say, okay, this is the first vertex. I'm just going to put it there. And I'm going to pick arbitrarily 3 neighbors to be these guys. And then you might think, well, okay, these vertices, they're also just, I mean, there's nothing special about them, so maybe they have high degree as well. Maybe they have lots of neighbors. And then you can just pick neighbors for them. Right? You can just keep going. And as long as you always hit vertices which have high degree, you can just carry on. So it's not a proof, because why do you always hit vertices of high degree? Well, you might not. You don't know anything about this graph, right? Maybe half the vertices are very high degree and half are very low degree. I mean, maybe this graph is, well, okay, I mean, who knows? So, what can we do about this?
Try to find a subgroup that only have high degree.
So, very, very good idea. Let's do exactly that. So, lemma 1. So if G is a graph with average degree D, then there exists a subgraph of G with minimum degree something. That's what we'd like, right? Where the something goes to infinity as D goes to infinity. Okay. Is the statement clear? I mean, modulo what we put here? If so, you should be able to prove it, because there's really only one way you can prove this lemma. Right? You have absolutely no choice in how to prove it. What do you have to do?
You get rid of the vertex with low
Yeah.
degree.
If there's a vertex whose degree is less than, what should I put here? I'll put x for now. Okay, and then we'll figure out what x is. X is some function of D. If there's a vertex with degree less than x, that vertex cannot be in your graph G prime. Right? You have to throw it out. So throw it out. If there's a vertex with degree less than x in what's left, you have to throw it out. Keep going, just doing what you have to do. You have to throw these vertices out until either this process stops because you reach a graph with minimum degree x, or all your vertices disappear. Right? And if your vertices all disappear, well, it wasn't true. Right? Okay, so let's just do it. Okay, so let's see what happens. So let's just list the vertices in the order in which we threw them away. Okay, so V1 was the first one we threw away. V2 was the second. and so on. And suppose we got all the way to the end. Right? So what do we know about this vertex? It was the first vertex we threw away, so we know one thing about it. Yeah, its degree is less than x. Right? It sends fewer than x edges forward, because that's why we threw it away. What do we know about the second vertex? So it's slightly subtle. It's not that it has degree less than x. It's that it had degree less than x after we threw away v1. Right? We threw away v1 and we said we look at what's left. Is there a vertex of degree less than x? Yes, v2. So v2 might be connected to v1. So it might have degree bigger than x, but it sends fewer than x vertices to the right. And that's true of everybody. Every single vertex sends fewer than x edges to the right. So how many edges does G have? Yeah, that's fewer than x times n. Right? Because if you just count all edges which go to the right, you count each edge once. Right? Each edge, you're not counting each edge twice, like when you sum the degrees, you're counting the degrees forward. So you're counting each edge once. Right?
N is the size of the...
Yeah, n is always the number of vertices. Sorry. Whenever I don't say how many vertices a graph has, it has n vertices. Sorry. Yeah. Thank you. It's okay?
I don't agree.
Okay, good.
For example, that n is the same as the n in the Bn. I mean,
Yeah, yeah, it's the number of vertices, yeah.
Okay.
Yes, I'm just summing.
So
Oh,
you
yeah.
stop in the middle, right?
No, I go all the way to the end.
Okay.
This one also sends fewer than x edges forward. I mean, it sends 0 edges forward.
Okay.
Yeah. Yeah, once you get down below x, then you throw everything away. Right? Yeah, you're dead by that point. Okay, so if this is less than, so how many edges does G have? It's got average degree D. So it has how many edges? Almost. Yeah. This equals n times d over 2. That's the definition of average degree. Right? Sum the degrees, you count each edge twice. So what does this mean? This means that x is bigger than d over 2. So we can put here minimum degree d over 2. I mean, sorry, at least d over 2, I guess. Is it okay?
Sorry, what
Yeah.
do you mean exactly by edge forward?
I mean going to the right. So I mean an edge. So if you're V2, this edge is an edge backwards. Every other edge is an edge forwards. Yeah, that's what I mean. So V2 might have degree x or bigger, but we know it has, because it counts this one. But we know that if you just count the ones to the right, after you remove v1, then its degree is less than x. Okay. Okay, so this is what we wanted, right? So using this lemma, we can say that if our number of edges is very large constant times n, then we have a subgraph whose minimum degree is large. And then we can do the strategy we said. Okay. So the strategy we said works, but it's kind of messy to write down. So here's a nicer way to write it down, or a nicer way to prove that. So here's lemma 2. So these lemmas, they're worth remembering because they're not just useful for this proof. But this is a very useful lemma in general in graph theory. There are many times you start a proof by saying, let's throw away half the edges and get our minimum degree. Okay. Even though the proof is very simple, this is a very useful fact. Okay, here's another useful fact. Another piece of notation. I'll try and bring in notation gradually as we go along. Delta of G is the minimum degree of a graph. Okay. So graph minimal, this is written delta of G. Then G contains T for every tree T with let me put k minus 1 with k vertices. Okay. Proof. Mm-hmm. Say it again.
Grab a vertex and start building T on that vertex.
So like I said, so that proof I think does work, but it's messy to write down. So I want to use a different argument. So yeah, so I think that works, but let's instead try and use. So we have this very general statement. It should strike you that this could be proved by induction. Right? So we have a nice parameter that we can increase. When k equals 1, then it's immediate. When k equals 2, it's also immediate. Let's use induction. So trees are actually, if you have a problem about trees, the first thing you should try is almost always induction. Because trees, they're very naturally made for induction in a way that most graphs are not. So why are trees particularly good for induction? Second? Do you know?
There is always a vertex with degree 1.
Right. Trees have leaves. This is not always true in cold countries, but but here it is. So what's nice about leaves? So what's a leaf? A leaf is a vertex of degree 1. There's also a leaf. So what's nice about a vertex of degree 1? Yeah, you can remove it. And if you remove it, you've still got a tree. Right? It's a very useful property. So first, why does every tree have a leaf? True. And in this case, I think not. But good idea. Okay, so how do you prove it? So that is the reason, but how does the proof go? So I mean that is almost the proof. You just have to formalize it, right? So what are you saying? I mean, one way you could rephrase it is: look, you just wherever you are you're in the tree somewhere at a vertex. If you're not at a leaf, just like walk somewhere. Just kind of keep walking, and eventually you have to stop, right? Because you can't come back to where you started, so you have to fall off, and that was a leaf. So, okay, here's another way to say that. So how about we just, okay, we're at a vertex. Let's just take a maximal path. That's what you're doing, right? You're just walking until you fall off. So take a maximal path. This path is maximal. So this vertex has no neighbors outside the tree, outside the path. But also it's got no neighbors inside the path, because that would be a cycle. So this guy's a leaf. And actually so is this one. Right? So if you take a maximal path, you see that the endpoints are both leaves of the tree. So any maximal path has this property. It's okay? Okay. Okay, so here is our tree. And here is its leaf. And let's call the rest of it T prime. So, how does the proof go?
Take it out.
So take the leaf out, right? So we got T prime.
You can embed it in.
Right, you can embed it, right? T prime has k minus 1 vertices. So by the induction hypothesis, we can find T prime in G. This is our picture of G. Here's a copy of T prime in it. Now we need to extend it to T. So this is some vertex U. There it is.
Its degree is bigger than chi k minus 1.
Exactly. So all we need to do is we need to find a neighbor of U outside this copy of T prime. But this vertex, degree of U, is at least the min degree of G. So at least k minus 1. And how many vertices does T prime have? K minus 1. So it has at most k minus 2 neighbors inside. So it has a neighbor outside, and you're done. Okay? So with induction, induction works very well with trees. Did it make sense? If not, please ask. It's okay? Okay. And so now we're done. What have we proved? What goes here? That would be great, but unfortunately not quite that good. So right, so suppose we put C here. So then what's the average degree of G? So suppose that the number of edges of G is C times n. This implies that the average degree of d bar of G is what? Almost. C over 2. Which implies, by lemma 1, that there exists a subgraph G prime of G with min degree at least. Shout. I mean, it's easy. Come on. So play the game. 0 over 4, right? Just so I know I'm not talking to myself, right? Okay, which implies that T is contained in G prime if what? If C, yeah, so if K, if C over 4 is bigger than what?
C over 4 is bigger than k minus 1.
Thank you. So C should be, sorry, I'm an idiot, but you also messed up. We got something wrong over there. We put our 2 in the wrong place. the average degree, the sum of the degrees is twice the number of edges. Thank you. The min degree is c. So c should be at least k minus 1. Degree of k minus 1. Okay. So our upper and lower bounds differ by only a factor of 2. Which is pretty nice given that we didn't have to work very hard. So what do you think the truth is?
We're done now because
Well, I mean, we're sort of done, right? We did what we were trying to do, but now I'm asking which do you think of these two is. Do you think the truth is this one, or maybe it's this one, or something in between? Right? I mean, you should never be completely satisfied with what you have. I mean, always try and push further. Does this argument look tight to you? No, I mean, so this looks pretty tight, but this was a bit wasteful, right? At least it feels a bit wasteful. So, Erdős and Sós in the 60s, I think, conjectured that this was correct. So that in fact, this construction is the best thing for every tree. Yep.
The conjecture is that we have an equal.
Yeah, conjecture is equal. Yeah, sorry, so I should write it properly. I'll put it over here. I'll put it down here. Oi. Maybe a bigger one or something. Whether this is really the correct thing. Yeah, so maybe it's even this, because really there should be a sort of a small error here, right? Because of the error. Anyway. For every tree. So a proof of this conjecture for large K was claimed by several very famous people about almost 30 years ago, I think. The proof is supposedly hundreds of pages long and still hasn't been written down completely. So I'm not going to remember the names of all of them, but Szemeredi and Szymonovitz and maybe Komlosh and I've forgotten one. Aitai. Thank you. Yeah. So they have given many talks on this and shown the proof to the sketch whatever proof, and people are still fairly convinced that they can prove it, but yeah, they still haven't finished writing it. So the moral is it can be surprisingly difficult to take the final step, right? I mean, it was very easy to get this far, but getting rid of this final factor of 2 is surprisingly difficult. Okay. Yeah, maybe we can try to prove while we're here. There's a theorem okay. So the graphs with linear extremal number are exactly those without cycles. So which part have we proved so far? We've proved that way, right? So if t does not have a cycle, so I should really call it h, shouldn't I? Let me call it h, sorry. T is a bit suggestive. Implies that it's contained in some tree, right? Because trees are maximal acyclic graphs. Just add edges until you can't anymore, and which implies that the extremal number of h is at most the extremal number of t, which is big O(n) by what we proved here. Okay, so we need to prove the other direction. Okay. Like. This is really a theorem, I guess. I've got a theorem. So what we want to prove is the extremal number of a cycle is much bigger than n. So, I mean, this means this divided by n tends to infinity, but we'll prove an actual bound. It's just right. This is our aim. This would be enough to prove that theorem, right? So we thought about this a bit the other day. Let's think about it again. So how can you construct a graph with very high average degree, arbitrarily high average degree, and no copy of a particular cycle? So we've seen two ways so far. I've mentioned two ways, neither of which is going to be useful, but let's just recall them. So first, if k is odd, then you can just take complete bipartite graph. Okay, so that's boring. So let's assume k is even. Maybe I'll even write 2k to make it really clear. Okay. The other way, well, when k is 2, when we were doing C4, I told you the right answer was n to the 3 over 2. And I said the construction was some weird algebraic thing coming from a projective plane. So let's also not do that, because that's not going to be so easy to generalize. In fact, such constructions are known for C4, C6, and C10, and that's it. So let's do something simpler. Let's not construct it. Right? So let's, instead of constructing a graph with this property, which seems very complicated, difficult, let's just show one exists. Right? So what are we going to do? Yeah, we're going to pick our graph randomly. So how do you suggest we pick our graph randomly? So here's a suggestion. You can tell me why it's stupid. Let's just put all of the graphs with n vertices into a bag and pick one out at random. Why is that a bad idea? It could be very sparse, but what is it likely to be? No, it's not at all. No, it's likely to be the opposite. If you put all of the graphs with n vertices into a bag, and pick one out at random, how many edges is it likely to have? About half of them, right? There's no particular reason it should be very sparse. There's way more graphs with about n squared over 4 edges than there are with many fewer, many more. Right? Most of them have the right number of edges, or sort of half the edges. But that's way too many for this. Right? We're bound to get lots and lots of cycles. We want a sparse graph. And really we want to be able to control the density of our graph. So instead of doing it uniformly, we should use something called the Erdös-Ramsey random graph. Let me introduce it. So we're going to come back and study this thing a lot more later on, but I just want to show you that it comes up very naturally in the study of these kind of extremal questions. So. This was introduced in 1960 or so by Erdös-Ramsey. It's called GNP. So I need to define the vertices and the edges. It's got n vertices. And what are the edges? Well, the probability that a particular edge is in GMP is P for all edges of the complete graph on n vertices independently. So for each pair of vertices, you toss a coin. The coin is biased. It's probably P of being heads, 1 minus P of being tails. If it's heads, you put an edge. If it's tails, you don't. You know, independently for every edge. Sorry?
Kn is fixed, right?
Yeah, exactly. Kn is fixed. Yeah, so the n vertices are fixed. So they define this Kn. For each pair, you keep the edge of probability P. Yes, exactly. So exactly this graph P equals a half was how we showed the lower bound of the Ramsey number. Exactly right. So this is a generalization, and I should point out that typically we'll assume that P is a function of n. Right? So it is interesting when P is constant, but it's more interesting when P is a function of n. Okay? And we're asking questions about it as n tends to infinity. Oops. Okay? These are sort of general assumptions about that I'll use without stating. So, first observation about this graph is it's not a graph. Okay? It's a probability distribution over all graphs. Every graph on n vertices is assigned a probability by this GMP. So it's a distribution over graphs. But it's often useful to think of it as if it were a graph. Okay, so I'll talk about it as if it were a graph. But you should always bear in mind that this is just a shorthand for convenience. Okay, so it's really a distribution. So we're giving a weight to each graph. The weights add up to 1. But we sort of think of it as being a graph. Okay, and a random-like graph. Okay, so what do we want to do? We would like to choose P so that the number of edges of this graph is much bigger than n, and the graph doesn't have any copies of C2k.
Sorry, just
Yeah.
to make sure
Yeah,
I understand
please.
computation. You are considering that object as a measure on the spaces of graphs.
Exactly.
Okay.
Exactly. Yeah. Yeah, that's what it really means. Yeah. But I'll write things like the probability that there's a triangle in GNP. Right, so I mean the measure of the event that there's a triangle in the graph. Right, counted over all graphs. So sum over graphs that contain a triangle of the weight of the graph.
So you take the random variable that counts the number of triangles and you integrate that random variable.
So one can also do that, but no, I mean the indicator function of there being at least one. But sorry, you'll see examples. Yeah, it'll be. Hopefully, it'll become clear with examples. So we'll do one now. So we want So we'd like to choose P such that the number of edges of GNP are much bigger than n, and there are no copies of C2k in GNP. So really, we just need that these both occur with positive probability, as in the intersection occurs with positive probability. So, can we choose P such that this is the case? Well, to try and figure this out, first, how many edges does GMP have typically? Well, first, what's the expected number? What's the expected number of edges of GMP? So neither of those. So if I understood correctly, so p to the power n choose 2, no, not that, because we're summing, not p times n either. Right, counting number of edges. So the sum over edges of the complete graph of the probability that the edge is in GMP. So here I mean the edge set of GMP. Right? This probability is p. There are n choose 2 edges. This is equal to p times n choose 2. Moreover, what's the distribution of the number of edges of GMP? So this is perhaps, so moreover, the number of edges of GMP is distributed like what familiar random variable? The binomial, right? This is just a binomial random variable. Binomial n choose 2 p. Right? I'm just flipping n choose 2 coins, probability p each. And so important basic facts about the binomial distribution is that it's very highly concentrated, right? There's a law of large numbers. So the first law of large numbers you ever learn, at whatever point you learn it, right? The binomial distribution looks like this. This is the average, and the width is small. So if this is binomial np, then this is p times n, and this is square root of p times n. Okay, so it's typically concentrated around its mean. So we can be pretty confident that, so with pretty high probability, or very high probability, the number of edges is pretty close to this. But the number of edges of GMP is very likely to be within a factor of 2, say, of this. Right? That's what this picture or the law of large numbers or whatever says. I'll go with this. Okay. So the edges of GMP is roughly Pn squared with high probability. Roughly meaning up to a constant factor. So for this theorem, we don't care very much about constant factors, right? We're just trying to prove something big. So this means if we're going to have any chance of this, we'd better take p much bigger than 1 over n. Right? Does it make sense? Right? We're going to have Pn squared edges, so we better take p bigger than 1 over n if we're going to have more than n edges. Okay. Now, let's think about this event. The event there's no copy of this cycle of length 2k. How are we going to control that event? Well, what did we do last time? I said there's this standard technique which is extremely useful in these kind of situations. Is that when you're faced with asking whether a random object contains something or not, you should instead count the objects. Right? So we should define a random variable, x, which is the number of copies of CK, exactly, C2K in GMP. And then we should calculate the expectation. Right? So, what's the expectation of x? So remember, we're going to use the fact the expectation is linear. So this is the sum over all copies of C2k in Kn of the probability that this particular copy of C2k is in GMP. Right? Which is let's say, so I'm going to use this, this approximately equal symbol to mean up to a constant factor. Okay, because I don't care about constants in this particular problem. So what is this? What is this sum up to a constant factor? What's its probability? Almost. To the power, right? Yeah. Right. There are 2k edges. They've all got to be present. Each one's present probability p independently. And how many copies of C2k are there in Kn? Up to a constant factor. K is a constant. Right? This is. So this is k is fixed and n is going to infinity. Okay, so to a constant factor depending on k, how many copies are there?
N to the k.
Almost. How many vertices does it have?
Oh, and
Yeah, n to the 2k. Right. Right. So you pick 2k vertices. It's like n choose 2k ways of doing that. Okay, but then there are many ways of putting the cycle in. But I don't care about the constant, right? There's a constant of in the n choose k, n choose 2k. There's a constant number of ways, whatever. Just it's roughly n to the 2k. Okay, times some constant factor that I'm ignoring. And why am I ignoring it? Because how large is this? Well, this is p times n to the 2k. P times n is much bigger than 1. So this is much bigger than 1. So meaning it tends to infinity. Right? So perhaps I'll rewrite this. P is much bigger than 1 as being p times n tends to infinity. This also tends to infinity. So the expected number of copies of C2k is large. Now, does that mean that there will be a copy of C2k? Not necessarily, right? So if the expected number is small, it means you've got some chance of not having one. But if the expected number is big, it could be that you almost certainly don't have one, but with some small probability you have vast numbers of them. Right? So we'll discuss this more when we talk about GMP in more detail, but unfortunately in this case that's not true. So here the expected number is big because you really get them. Right? You really will get copies of C2k. Okay, so the proof method has failed. Right? We tried to pick P such that it has these two properties, and we failed. Right? Because in order to get this means P has to be bigger than 1 over n, and therefore you get copies of C2k. Okay, so we're dead. So we failed. So let's give up and go home. or not. Maybe we can modify the proof somehow. So can you think of a way in which we could take this failed proof and change it or augment it or do something to make it work? In order to show that this graph exists. We want to find, not even find one, we want to show that there exists a graph with these properties, with way more than n edges, and no copy of C2k, and I want to use what we've learned about GMP to do it. I don't just want to forget this, I want to say, okay, it didn't work as we wanted it, but actually this is enough. What can we do to show that this is really good enough?
What if you ask less, for example, pn squared, you change the exponent to something smaller, like close to 1, is bigger than linear, but not.
I mean, for it to be bigger than linear, we need this property. Yeah. Otherwise, it's so as you could ask, but if we take p smaller, but say there's some small probability that it has way more edges. But if it's got way more edges, then it's already as if you'd taken p bigger. It doesn't really help. So what has this proof given us? This proof is, what has GMP given us? We haven't found a graph with many edges with no copies of C2k. But what have we found? We found a graph with lots of edges and not. So
Well, I was thinking it has lots of copies of.
it has lots of copies of C2k, but not that many.
Yeah.
Right? It goes to infinity, but quite slowly. Right? When Pn goes to infinity slowly, this also goes to infinity slowly. So we have this graph. It's got the right number of edges for us, and it doesn't have very many copies of C2k. What do you want to do with those copies of C2k? Yeah, erase them. Right? Just throw them out. And then what are you left with? Yeah, but still has lots of edges. And that's the proof. Right? Okay, so let's do it. Right, so that failed, but so let's just choose P such that what? So your number of C2Ks you expect is about Pn to the 2k. What's that? Smaller than something. What's going to be enough for us? Or much smaller than, if you like. How many C2Ks can we get away with? What are we going to do with them? We're going to throw them out. That means what? What's the simplest way to destroy a C2K? Just remove an edge. Pick one edge of it and delete the edge. So if we do that for every copy of C2K, we'll have deleted Pn to the 2k edges. How large can we afford that to be? I mean, if it's smaller than the number of edges we have, then we don't really care. Right? So as long as this is much smaller than Pn squared, then we can safely remove one edge from each copy of C2k without having deleted many edges. Right, we still have more than half the edges we started with. We don't care about constant factors. Right? So what's that equivalent to? This is if and only if p to the 2k minus 1, n to the 2k minus 2 is much smaller than 1. So p should be much smaller than n to the minus 1 plus 1 over 2k minus 1. I think that's right, isn't it? Okay, let's just call this epsilon. Right, so let's let p be equal n to the minus 1 plus epsilon. Right, so we're going to get, this is the bound we're going to try and prove. Okay, what we want is, we want with the GMP with high probability, so suppose I write lemma, with high probability of the following two properties: the number of edges of GMP let me put it in there. Edges of GMP is at least, let's say, Pn squared over 100, whatever, and the number of C2Ks in GMP is at most so times something. So I want to say that both these things occur with high probability. High probability is going to mean probability tending to 1 as n tends to infinity. Okay? So why is the first one true with high probability? Yeah, it's much smaller than the mean, so this is just the law of large numbers. Right, so I'm not really sure how many people are happy with that explanation, and how many people would like me to explain more. So who is happy that this is just the law of large numbers? Nobody. Almost nobody. Okay. So, right. Okay. Let me expand on it a bit. I'm not sure you're going to be happy with this explanation either. So we'll see an inequality, to Chebyshev's inequality a little bit later, which also proves this. But here's the sort of the correct bound. This is the real behavior. This is proved by Chernoff in like 1950 or something. And what does it say? It says basically the probability that a binomial random variable, NP, differs from its mean by at least t is at most e to the minus t squared over, there's a constant here that I don't always remember what it is. I think maybe it's the 2 times the mean. Okay, so what this is saying is, I'll just draw a picture of it. It's just the picture I drew before. So here is binomial NP. here's the distribution. The top is basically at p times n, and the width of this thing is like root p times n. Okay? So once you get above root p times n away from the center, you start decaying super exponentially quickly. Right? So as long as Pn is big, so root Pn is much smaller than Pn, then you're very likely to be within a small constant factor of the mean. Right? The binomial random variables are very nicely behaved. They look like normal random variables, basically. Is it okay? So I'm not going to prove this, though the proof is some very simple analysis, actually. So in a probability class, I guess they'll typically prove this. Is it okay? So this is just a standard fact about the binomial distribution. Please.
Your big N
Yeah.
is
Any number.
okay. You are not denoting N to choose 2.
So I'm perhaps thinking about it as n choose 2. But this is just a fact about any n, but just about the binomial distribution. But yes, we will be applying it. We're applying it here as n choose 2. Exactly. So yeah. So this Chernoff implies this with capital N equal little n choose 2. Exactly. Yeah. Okay. Who is now happy about this? Who would like me to go into even more detail about Chernoff's inequality? Nobody. Okay. Yeah, I also don't want to go into more detail about it. Okay. So now, why is this one true? And what do I want to put in place of question mark? All right, so we really want to put here like big O, right? Some kind of a big O.
Also one of Markov, something like that?
Yeah, so this is just Markov, exactly. So here's a more basic inequality. Which we can prove very easily. It says, okay, so let's let x is going to be a random variable taking non-negative integer values. So like all of our random variables in this course, they're all just counting something. What do we want? We want something about the probability x is bigger than a, say. I'm going to write t instead. T is at most what?
Expected value of x.
Exactly. The expected value of x divided by t. And what's the proof? Well, what's the definition of expectation? The definition of x is just equal to the sum over k equals 0 to infinity of k times probability x equals k. So let's just cut this off at t. So at least the sum from k equals t to infinity of k times probability x equals k. And now k is at least t. This is at least the sum from k equals t to infinity of t times the probability x equals k. But now this just equals t times the probability x is at least t. And that's that. Okay, so we just ignore things being smaller than t and ignore the fact that k is bigger than t. Right? So it's sharp only if the weight here is all on t. Okay, this is a very easy inequality. That's exactly what we need here. Right? Because this is saying, what's the probability that your 1,000,000 times the expected value is at most 1 over 1,000,000? Right? This is the expected value. So what's the probability you're not within almost 1,000,000 times it is small? Right? So this occurs with high probability by Chernoff. This occurs with high probability by Markov. And this calculation that we did. Right? Okay, so GMP has these two properties. We chose P such that this was the case. Right? So, if GMP has this, so here's an important point. Right? This lemma is about a probability distribution. It's about some measure. But we want a graph. So what do we have to say? All we say is, this occurs with high probability, therefore, it occurs with positive probability, therefore there is one graph with these two properties. Right? That's all we're going to use. It occurs with high probability, but all we want is this one graph with these two properties. And then given this graph and this property, we can remove one edge from each copy of C2k without destroying many edges. And then we're done. So what have we proved? We've proved it's basically at least n to the, so it's like Pn squared, n to the 1 plus 1 over 2k minus 1, okay, times some epsilon. Yeah, please.
You have high probability
Yeah.
on the first part and high probability on the second also.
Yeah.
But why the intersection has also high probability?
Good question. So high probability means that what's left over is small. And what's left over here is small. And small per small is small. So in this case, it's OK. But yeah, in general, you have to be careful. Yeah. Yeah, so it would not be enough to say they both occur with probability at least a third, because then the intersection might be empty.
You only need a positive probability, right?
And all I need here is positive probability,
Yeah,
exactly.
I mean, if you have a set A with probability bigger than a half and B with probability bigger than a half, I
Yeah.
think the intersection has.
Yeah. So that's exactly right. Exactly what we're using. So really all we're using is both of these have probability at least a half. Or even less, the sum of their probabilities is bigger than 1. Yeah. OK, yeah, please.
Why we first say that B is like way less than n to the minus 1 plus epsilon, but in the lemma is equal.
I put an epsilon here, which is supposed to be a very small constant. It's supposed to be small enough to make this sort of, make things small enough. So I'm cheating slightly but with this notation. So if you like, I don't know how you want to state this otherwise. Take epsilon to be something going to 0 slowly. And then I proved it, I guess. Yeah, but really we've proved it with some fixed constant here. If you really do this proof, I mean, being more careful, then you get some fixed constant here. Like 1 over 10 or something. I mean, nothing really terrible. Because I guess, as was pointed out, you don't really need high probability here. You just need, yeah. I mean, here you really need positive probability. Probability enough to beat this. Yeah. I'm not sure exactly what the right way to optimize it is. Because, I mean, this isn't a sharp bound anyway. Or, yeah. So this is known not to be sharp anyway. Yeah, so there's a random construction which beats this by a logarithmic factor, but it's much more complicated to prove it. Yeah, and in some cases there are algebraic constructions which beat it by more. Okay, but there was enough to prove what we wanted to prove. Okay, so we'll come back and we'll do more proofs a bit like this a bit later in the course. So for today, I'd like to talk a bit more about things related to trees and related to planar graphs. So here's a question. So definition. So a graph is planar if you can draw it in the plane without having crossing edges. Ooh. Cruzando. Know that? Okay. So, examples. The graph with one vertex is planar. Also with one edge. This one also. This one also. This one also. This one also. How about K4? Yeah. So I didn't say they had to be straight lines. Though you can always do it with straight lines. So K4 you can draw with straight lines like this. How about K5? Why not?
You have to add the point K4. There's nowhere to add it.
Yeah, that looks like a proof. Maybe it is a proof. I'm always a bit confused with planar graphs. Anyway, let's give a different proof. So here's a problem, which will lead to a proof. How many edges can a planar graph with n vertices have? Right, so the same question as we've been asking, the same extremal question. What's the maximum of edges given this restriction? So I think it's also not so obvious how to do it. So here's a useful lemma. Due to Euler, maybe Euler, which probably you've seen before. V plus F is E plus 2. Right. What does this mean? So perhaps this is the name of the lemma. So the number of vertices of G plus the number of faces of G is equal to the number of edges of G plus 2. So this is the number of faces in any planar drawing of G. So any drawing of G in the plane, this lemma says you have the same number of faces and it satisfies this identity. Okay. So let's try and prove this lemma. Induction, what a good idea. On what? Suddenly now we have some choices. On E. That's a good idea. What's the base of your induction? E of G is 0. It can be, it's connected if the number of vertices is 1 or 2. So the number of vertices is 0. Then I'm not sure we know what the number of faces is. Let's assume we have at least one vertex. How many faces do we have? 1. And we're OK. The number of vertices. And the vertices, you can't have 2 vertices, then you're not connected. OK. Yeah. Sorry, just.
So how exactly do you define the face? I mean,
Yeah. So this is a good question. So in given a plane drawing, so given a drawing of a graph, then it's just a connected subset of the plane. F of G is not obviously defined before you prove this lemma. Right? So this lemma is proving that f of g exists, and then it's this. Yeah. But giving a drawing, I hope it's yes. Believable. Same. Yeah. So the definition of the number of faces is exactly. So here's a graph. How many faces does it have? This is a connected region. That's 1, and the rest is another connected region. So 2. So it's the number of disconnected subsets of the plane, disconnected by the graph. Okay.
Se não tem nenhum vértice, aí a mais fácil seria 2.
Yeah, I think we're assuming it's got at least one vertex. I guess.
We could try to do something similar to that
Mm-hmm.
that we did with the tree.
Uh-huh.
So when we have a vertex of degree 1,
Yeah.
we can take it.
Mm-hmm.
We can take one vertex and one edge, and it doesn't affect the
Yeah.
faces.
Yeah, very good. So, case 1. So this is the degree of a vertex, the number of neighbors. There exists a leaf, vertex degree 1. Let's remove V. What happens to the different numbers? The number of vertices goes down by 1. The number of edges goes down by 1. We claim we're left with a graph with one fewer wherever this plane of this guy happens to be, he's not going to change the number of faces. Right? Because, yeah, so if you have a vertex degree 1, whatever is happening in the rest of the world, removing him doesn't disconnect or connect anybody, because these guys are already connected to each other. Right? So it doesn't change the number of faces. stays the same. Right? So therefore this is true therefore this works by induction. Right? Okay. What if there does not exist a vertex of degree 1? Yes, why is that? Because there's a cycle. Yeah, so we already showed that every tree has a leaf. More generally, any acyclic graph has a leaf. Right? Okay, so if the graph has no cycle, then we can take a maximal path, and the end vertex is a leaf. So if there does not exist a leaf, there exists a cycle. And if you remove an edge from a cycle, so here's your cycle, here's your edge in your cycle, here's G. We claim that the number of, so we have to claim various things, right? So as I'll do it, I'm a very big fan of this drawing. So here's G. Here's an edge that's in a cycle. Okay. So if you remove E, what happens to the number of vertices? It's the same. What happens to the number of edges? It goes down by 1. What happens to the number of faces? So the claim is it goes down by 1. And what's the proof? So this side of the edge is in some face that must be contained in this cycle. And this side is contained in a face which is not contained in the cycle. So this side of the edge and this side are in different faces. When you remove it, they become the same face. Okay. We're going to check one more thing. What is there left to check to finish the proof? Yeah, exactly. We need to check that G is connected. Why is G connected? Sorry, G prime is connected. G prime equals G minus this edge. Yeah, exactly. So any path we want to show, so we know G is connected. So any two vertices, x and y in G, there's a path that connects them. If the path doesn't use the edge E, it's still there. If it did use the edge E, we can use the other part of the cycle. Okay, so it's done. So that's the proof of this famous lemma.
So when you're proving that, you're assuming an embedding of the graph already, right? Like the graph's drawn and then you work with that.
Right. So what's actually happening? This is a good question. So in this case, there's a vertex of the graph. It's not in the plane yet. There's a vertex of the graph degree 1. So I remove that vertex. We're given some graph, and however we embed that in the plane, we know it satisfies this inequality, and f is defined. And now if we add this edge back in, we know it doesn't change the number of faces because it's just a leaf. So then it says, sorry. No, I'm saying this wrong, aren't I? You're quite right. I want to prove that however we draw G in the plane, thank you, however we draw G in the plane, we get the same value for f. Yeah, so we draw, exactly right. So we draw G in the plane, and we see this edge somewhere. And we say, okay, we know how many faces this thing has. if we remove this edge, then now we know how many faces, we know we have the same number of faces, and it must be defined by this guy for G prime, because by induction we've already proved that. Yeah, so you're quite right. Yeah, and then here similarly, we have some embedding of G in the plane. Then we remove this edge, and now G prime we can apply the induction hypothesis to. We know that then f of G prime is we know this thing exists. And then when you add the edge back in, you change these things by 1. Yeah, thanks. Yeah, that's that. More questions? Yeah, thank you. That was a good question. OK. Right. Now, how to deduce a bound on the number of edges in a planar graph? Good observation. So let's let G be planar, and also let's assume it's maximal, so the most number of edges. So we can't add any more edges without stopping it being planar. That implies it's connected. Because if it was disconnected, then we could add in that edge. Okay, very good. So we can assume it satisfies the conditions of the lemma. This implies that V of G plus f of G, V of G is n, equals E of G plus 2. We need to get rid of this f. What can we do with f?
Each face is made up of at least 3 edges.
Right. So this is almost true. Can anyone give me a counterexample to the claim that every face has at least 3 edges? Say it again. There's more. I mean, I want an example of a face with fewer than 3 edges.
The point, only one vertex.
Yeah. Here's an example of a face with no edges. And here's one with 1 or 2, depending on how you count. So let's assume n is at least 3. I mean, we can solve the case n equals 2 by ourselves, right? So, and n equals 1. OK, so if each face now has at least 3 edges sitting on it, so if we take 3 times the number of faces, that's equal. It's a most, yeah. Yeah, exactly. Good. Right, so here we're counting each edge from both sides, right? So each face, each of the 2 faces can count it, or if it's in the same face, I guess it counts it twice.
G is maximum, so every face has exactly 3 edges except. No, yes, there's.
Yeah, so this will also be true. Yeah, so exactly. So yeah, you can also add. Yeah. Yeah, so that's true. So in fact, it will be equal, but perhaps it takes a little bit of argument. Anyway, this is definitely true. You're right. OK, so what does this tell us? This implies that E of g plus 2 is at most 2/3 E of g plus n. So E of g is at most 3n minus 6. Is that okay? Right. F of g is at most 2/3 E of g. Pull it over, n minus 2 times 3. And just observe, this is not true if n is 2 or 1. Right. So we did need the condition n at least 3. But otherwise it's sharp, and you get equality if and only if G is a triangulation. So a planar graph in which every face is a triangle. Okay? Right. Now, 3 quick consequences, or perhaps just 2 quick consequences, and a question. Corollary, K5 is not planar. Proof, yeah, 5 choose 2 is bigger than 9. Right. 15 minus 6. Question. Is K33 planar? K33 is this guy. It has 9 edges and 18 minus 6. What am I talking about? Am I talking nonsense? It's 12. But it doesn't look very planar, does it? I mean, you can do this to get the first 2 of them, but then where do you put the third one? It's got to be connected to these 3. It can't go here, can't go here, and it can't go outside. So what should we do here? What extra property of K33 can we use to show it's not planar? Thinking about the proof. What happened in the proof? We had some identity, and then what do we say here? We said every face has at least 3 edges. What can you see about K33? It's got no triangle, right? So every edge has at least 4. So if it's triangle free, we can place this by a half, and then instead we get 2n minus 4, and 2n minus 4 is 8. Okay, so K33 is also not planar. Okay, and one more observation. So, I don't think I defined this yet, so let me define it now. Well, it's gone. So what is the chromatic number of a graph? Chi of G is the minimum number of colors such that there exists a coloring of the vertices of G this time with our colors such that C of U is not equal to C of V if UV is an edge. So we've already sort of seen this number when we were looking at these extremal in Turan's theorem, for example. We're looking at bipartite graphs. Bipartite graphs are exactly graphs with chromatic number at most 2.
Excuse me, what is written there for all?
For every UV, it's an edge of G. So if you have an edge of G with endpoints U and V, then the endpoints should get different colors. Yeah, so for every edge, you're not allowed to have a monochromatic edge. You're not allowed to have the endpoints the same. So what can you tell me about the chromatic number of a planar graph? But when you think about that, I'll tell you just one more thing that I forgot to say here. So why did I pick K5 and K33? Why do I care about these two particular graphs? It seems a bit boring. But in fact, these are two very special graphs. So it turns out that planar graphs, which sort of have this slightly strange definition involving the plane, which is uncountable and therefore shouldn't appear in this course at all. In fact, a graph is planar if and only if it avoids these two graphs, but in a slightly generalized sense. So theorem, this is an old theorem, and I always forget. There's two versions, I forget who is who. I also forgot their names. Wagner, Krotowski, I've forgotten. Anyway, so G is planar if and only if does not have a topological copy of K5 or K33. What is the topological copy? Well, you take your K5, and you can add some vertices onto the edges. So you replace an edge by a path, basically. It's also if and only if it does not exist so-called minor of K5 or K3 in G. What does that mean? A minor means you have 5 connected sets representing the vertices, and then there's at least one edge between each set. Okay.
Just connected.
Just connected, yeah. So this is a K5 minor. This is a topological K5. Turns out actually either is enough to characterize the planar graphs. Yep. So you take your graph and you replace each edge by a path. And the path should be vertex disjoint. So you don't have to go in one, in one, you can go in many steps.
So there are arbitrarily big k5 topological.
Yeah, exactly. It could cover the entire thing. Yeah, so in particular, this thing is not, you can see it's not planar, because these vertices don't matter at all, right, for deciding if it's planar. You just delete them, and then you're left with the k5, and it's not planar. And the same thing here, right? You could sort of contract these things down to vertices, and then you're left with a k5, so it's not planar. So it's sort of clear that both these things are not planar, and in fact, this is enough to characterize exactly the planar graphs. It turns out, moreover, that for any surface, then there exists a finite set of forbidden minors that characterize the surface. This was proved in a series of about 20 papers over the course of about 20 years by Robertson and Seymour. So it's quite extraordinary, like hundreds and hundreds and hundreds of pages of sort of lots of clever ideas mixed with lots and lots of analysis of cases. It's basically they steamroller the theorem. They just sort of demolish it by sheer power and force of will. Yeah, it's really quite extraordinary. Yeah, so they developed this big theory which solves this problem. This was one of their main aims, and also solves some other famous problems in the area. So related to the chromatic number of planar graphs. So there's a couple minutes left for you to at least tell me something about the chromatic number of a planar graph. What bound can you prove easily? Maybe it should be homework. Okay. Yeah, so homework is prove some upper bound on the chromatic number of a planar graph. Maybe I should help you. You should definitely prove 6. And if you can prove 5, I'll be impressed. Don't try and prove 4. Even though it's true. Yeah.
G is
Planar, yeah, sorry, planar. Okay, so yeah, for homework, I mean, it shouldn't take too long. Prove 6, and then at the start of next time I'll prove 5, and then we'll see. I'm not sure what we're doing next. Yeah, please, everybody send me an email. Once I've received, I don't know, enough emails, I'll send you the first lister. In the worst case, tomorrow night I'll send it to whoever sent it.